So yesterday we did, theory, and we did simple model, etc. And we came up with, somebody asked about, I think it was Rick, you could talk about false positives, and we got to one of them, which was, well, low saturation gas is going to give you a problem, right? So we know that. You can misinterpret that very easily. You think you have a commercial reservoir of amplitudes, and you don't. Today, we're going to talk about another fly in the ointment, another complexity, and how you deal with it and what its consequences are. That's the first thing out of the box here. That's composite rocks and laminated model. And immediately, there we go.
I think it's on that.
Yeah, that could be it. Here's a picture of a core in I don't know, polarized light as well as regular light, ultraviolet. And I want you to notice this thing first, 18 inches. Okay, look at the scale. This is a deep water deposited rock, and it's a reservoir. And what do you have? You have a nice interval of very good sand, some decent sand here, another nice interval of sand, etc. Okay, so and then you have these fine grained rocks that are impermeable interspersed with them, all layered. This is what deep water deposition looks like quite commonly. And again, the scale here is 18 inches. The resolution of a normal sonic tool is 2 feet. That is, can't resolve anything less than that because the receivers are set 2 feet apart. And even though they sample them at every half foot, let's say, so you could deconvolve them a little. You can't deconvolve to any better than 1 foot. Now, Schlumberger is, if you want it, they'll put out a sample every 10th of a foot if you ask for it, because they ping it a lot more often. They just sum the pings. And so you could deconvolve some more if you wanted to, but nobody does it. So just be cognizant of the fact that all of this will not look like anything serrated at all on your log response. In fact, what we have here is something that looks like this. It's just a cartoon of what you just saw. And this is a slide I'll spend some time on. I'm going to start at that end. And even this slide is, which I say idealized, it's worse than the picture in this slide shows you. This is a deconvolved and integrated seismic trace, a run-sums trace, okay? It's supposed to look like a log, but a very severely band-limited log then, okay? A log rho V log. Band-limited log rho V log. If you had a wireline log that corresponded with this, and you converted it from depth to time, let's say, or vice versa, converted this from time to depth, so that these are all on the same scale, you might see something that looked like this. In fact, the log would be, would have much higher frequencies than this. That one you're just looking at relative to this loop. So I've already tempered the comparison. And you might have in here, I don't know, I'm drawing this with colors, etc. Let's say I had some oil here and a gas on top of it, oil and gas, and a gas sand and a little oil underneath it with a shale string. So, you know, some character of that nature. Well, let's just open this baby up and look at one of these reservoir units. At that point, there are individual components. If you're a petrophysical engineer or a reservoir engineer, you start doing, for reservoir simulation or calculations of reserves, how much have I got there, things like that nature, you start breaking these log responses up into, this might be 50 or 60 feet thick. And Mike just told you, we calculated yesterday, if your typical seismic is, say, 10 to 50 hertz. 50 hertz at 10,000 feet per second, that's a 200-foot wave. Okay, so you have very large loops with respect to even, say, a 50-foot reservoir. So here I break this up into whatever number of units I have, which are resolved by the law, which I think are higher porosity or lower porosity or what have you. And that's what these represent. It's a multi-purpose slide. And if I took any one of these intervals That's what I was talking about on the last slide. This interval might be 4 feet thick or 5 feet thick. It's 1 out of 10 out of a 50-foot unit. And that, going back, that 4 or 5 foot looks like this when you get up close and personal. But you don't see this. What you see instead is this. So here's the next cartoon. Suppose I had a clean reservoir rock. So in that little core picture, at the top we had a sand, down here we had a nice clean sand. Suppose I had a massive sand like that, and such sands exist in deep water deposition, by the way. What would my BP log response, idealized log response look like? Oh, I'd have some background here. And when I get to my clean sandstone, I'd have a nice, continuous, flat-looking sand. And if I looked at my SP and my gamma ray, they too would be flat. I said, boy, not a nice sand. You just got done looking at this, and you see some units that are nice and continuous there and have stable log responses across a number of logs. What would this thinly laminated core look like on this VP log? Well, it would look something like this. It would look like a fat sand, and it would look different on the gamma ray log, just as it looks on the VP log, in the following sense. You notice over here I'm at this velocity, but here I'm not quite at that velocity anymore. And the same thing on the gamma. I would have a lower gamma ray in that guy than I would have in this guy. By the way, the gamma ray has a variable resolution depending on what speed you're running the log at, but it's typically similar to the sonic. So that means that we can't really resolve this fine lamination. And we have to somehow handle, well, what will be the response of that to fluid substitution? Suppose I have a laminated rock that has some fraction of sand and some fraction of impermeable shale or siltstone interbedded with it. And this is something to remember. I generally talk in terms of sand fraction. Sand fraction is equivalent to what is often called and used, and I think BHP Bulletin uses this term, net to gross. Okay, your net to gross reservoir is the same thing as the sand fraction of that laminated unit.
And also, for those from a mining background, that this ends up being very analogous to your sort of assay. In other words, if you have sort of a gross size of an ore body, and then they'll talk about what percentage of that is actually iron or nickel. And again, it's very similar here because it's an assay of in terms of the gross interval, how much of it is actually reservoir rock.
Okay, well, the density, pretty simple. If I know the end members, the shale and the sand densities, properties, then it's pretty easy. It's just a linear combination of the two. That's what I would see on the density log. Now, for the velocity, the vertical velocity through, first of all, velocity through a sequence of layered laminated medium with laminae that have different elastic properties. It's an anisotropic medium. It will have a different propagation velocity in this direction than it will in the vertical direction when you have much horizontal plates. So I'm not going to get into the anisotropy, that's all worked out. And suffice it to say that the vertical velocity through a stack of horizontal plates, if you know the properties, the rho and VP, let's say, of the end members, works like this at low frequencies. So the low frequency response of a stack of these laminated elastic bodies looks like a single anisotropic medium, the vertical velocity through which is this. 1 over rho VP squared equals the sand fraction, or net to gross, over rho sand VP sand squared, plus the shale fraction over rho shale VP shale squared. And the same would be true of the vertical shear velocity. That is, we just replace the P with the S. So that's given by Postman 55, and probably earlier than that for all. But anyhow, that's what it looks like. Now, What is that?
Sorry. And
Yeah.
what was low frequency? Are you still considering anything under the megahertz range as low frequency?
Yes, for sure. Low frequency would mean anything that has a wavelength that is longer than let's say a laminated body, the frequency or the cycle of the laminations. So if I had 10 laminations that were, let's say, 10-foot sand, and in this case we had 18 inches or 24 inches, and we had about 10 cycles there, right?
Yeah.
That would mean that anything that had a 1 foot wavelength would already be a low frequency. 1 foot wavelength or longer would be a low frequency. This would correspond to it. The high frequency limit, of course, would be, let's say you had things that had a wavelength of a millimeter, very high frequency sound. Then what would happen? Then you do what is called time average equation, would give you the velocity. So instead of this equation, you would say, well, I simply take the sand fraction times the transit time in the sand, and the shale fraction times the transit time in the shale, and that gives me the transit time through the whole body, and the inverse of that is the velocity through that body. Because when my little pulse that's got only a millimeter wavelength is in a 1 inch or 1 centimeter or something like that laminate, it doesn't know that there are boundaries on either side. It's isolated from them, so it just travels with the velocity of the shale, and it only knows what speed to travel at from its immediate surroundings. So that's the way to think of it.
Yeah, but I think you have pointed to, this does get more sensitive, and it's really the upscaling problem you hear a lot of reservoir engineers talking
Often
about.
called that.
Is that this is the proper way to upscale to the sort of the seismic level, and then there's a different upscaling that the seismic will go and average in a different way in something that's sort of above it. So it has to be in reference to the wavelength at which you're sensing it, and there's a different way that things are sort of effectively upscaled, below that wavelength and size, and a different wavelength that is done above that size. So it is one thing that you do need to be careful of when you're working through these type of issues.
So anyhow, we're going to calculate what this looks like for some kind of a medium. And I'm going to take an extreme case just for example. This line doesn't mean anything, but what we have here is two media with equal velocities, but number two has got half the velocity that number one has. Okay? So that the velocity of number one is twice the velocity of number two. Now, when you're looking at sedimentary rocks in the log, you don't see contrast that big. So this is a very extreme case. But you also don't see them with the same density. So this is nothing but a straight line connecting the two endpoints. Okay, and what we're looking at is the concentration here at the bottom concentration of number one, P1, because it's over here is the higher frequency. Okay, so the high frequency curve, the time average curve of what the velocity would be for such a stack of plates would be this curve. The low frequency curve would be that curve, and clearly that's monotonic, but not just linear. So you would not have just a linear velocity. Okay, let's look at
Point down. You're pointing at the computer.
Yeah. Okay. We can change the density using the Gardner-Gregor relation. Same kind of velocity concentration. These things separate a little further. This is just for your information. I'm not going to dwell on this. So here's a question. What happens if one does fluid substitution in a laminated reservoir rock as if it were a homogeneous reservoir rock with the same brine saturated density and velocity? So you say to yourself, oh, I got this log. Remember the cartoon I had over here? I have this log, and that looks like a nice pig to me. And I'm going to call that a homogeneous sand, and I know what the density is, and I know what the velocity is from the log. Now I'm going to do my Gaussman substitution as if that was a homogeneous rock. Okay?
Okay.
You get the wrong
Like,
answer.
but yeah, not all of your laminates have the same porosity. So
That's correct,
if you-
but you don't know that. You don't know that. All you know, let's go back. All you know is this. So you said, I think this is a homogeneous rock, and I think the density looks like this, and I know what those values are, and I'm gonna treat it as if it was a homogeneous rock, okay? Let's just say a poorer quality sand than my best quality sand. Remember we picked end members, we talked about end members yesterday? I didn't tell you all this yesterday, but there's a reason why we don't try to pick every sand, but try to pick those with extreme properties, the shales and the sand. And it has its own problems too, and we'll talk a little bit about that toward the end. But that's what we're doing here. Here's an example case. It's a real example. It's not contrived properties like the high frequency, low frequency slide I just showed you. And in this case, I'm looking at water saturation of 0.2, methane gas, 30 degree gravity oil, you know, half saturated with gas, etc. The real numbers. And we have net to gross at the bottom. And this is just the density that I'm calculating. This is the correct density for the laminated model for this particular pair of shale end member sand, excuse me, properties that came off a log. And this is, I think, Atlantis, came from Atlantis. And these dash curves are what you would get for the oil and the gas if you did the substitution, assuming this guy is a homogeneous rock with the velocity and density that it actually has, which are given by the laminated formula you just saw. And so what's that look like? Well, what did you do? Let's go down to some place like 0.6 or something. This part of the curve you shouldn't pay much attention to. It doesn't really mean much. If you're down there at 10%, you're not going to pick it as a sand anyhow. You wouldn't be paying attention. You wouldn't be thinking of it as I would say, that looks a lot more like a shale or siltstone or something. I'm not even thinking that's a reservoir rock. With something in here, what have you done? You have biased your expectation. Remember our logic slide? Your calculated reflectivities, we're looking at just the density part here, but this will contribute to the reflectivity. You have biased them to a greater response than is correct for that kind of reservoir rock. That's what you've done. So in essence, you've made an oil look like more like what a gas will really look like. That's what you've done. Let's look at the velocity curve, and the same thing happens. That is, these things are pushed down. There's a greater response from this curve calculated than is in fact appropriate for that laminated rock. And this is, what is this? This is the shear. Notice that the shear has the same effect. You get a bigger effect. It's more pronounced. So the VP to VS ratio is also wrong. You don't get even the right VP to VS ratio. That's important for ADO, as you'll see later today. Okay, so let's imagine that we say, okay, we've looked at some cores, and we've looked at the logs, and there are clues on logs. Sometimes the laminae are thick enough so that you get an indication on the log that the response is a little rattier, what we call a little rattier. Your P10, P90 will be bigger in a laminated rock than it is in, let's say, a really nice, massive, clean sand. So you get some clues after you've looked at a lot of these, but they're only clues. So you say, I got to deal with this somehow, this laminated business. How am I going to deal with it? Well, gee, I've got the formulae. All I really need is the end member values. So if I pick the end member sands, the cleanest sands I have, I don't have that absolute scale we talked about yesterday in the trend curve lecture. I don't have that scale that says, boy, this is a clean quartzitic sand, there's nothing in it. I know which ones those are in the logs. I don't have core everywhere. And that's why I said check when you can. You do a relative, but you try to pick the most extreme responses, the least gamma ray, SSP development, et cetera. Those are your end member sands. And then you say, okay, that's one end member. Now I need the shale end member. And so you pick the best shales you could, highest gamma ray responses, most resistive, or depends on the kind of stratigraphy, the best shales. And you can make arguments, you can argue, and I'm not going to argue, about whether the very thin laminae have the same properties as massive rocks of the same type. They may have been laid down by different mechanisms, and so you can argue this. I don't want to talk about hell freezing over, but I didn't say it. You can argue it a lot. We don't have answers for that, but if you use the massive rock properties as your end member properties, then you can calculate what the responses will be for various sand fractions. And this is what happens for the density. It's pretty simple. That's just a linear relation. So this tells you what you would have. For the velocity, the way you do the calculation is say, okay, I'm going to take these sand members, which have clean, high porosity, and I know what those are, and I'm going to calculate the fluid substitution in just the sand. And then I'm going to put that oil or gas saturated velocity and density together as one of my end members with the shale velocity and density in that laminated rock formula you saw just a few slides ago, and calculate each point on this curve and then each point on this curve. That's how I'm going to put this. I'm going to make this. Question?
Yeah, so you're just saying that the fluid is only in your sand, but not in the shale.
I'm sorry?
So you're just saying that the sand has a lot greater capacity to soak up the stuff than the shale does.
I can't hear you, John.
So you're just saying that the fluid is only in the sand, right?
Yes,
Yes.
exactly. Just doing the fluid substitution in the sand and then laminating that with the shale end member property. This is what you get. So let's look a little bit at this. I think I have, this is the velocity. We looked at the density. Let's look at the reflection coefficient. I haven't showed you the shale. I might should have put it on here. Excuse me. But it's not easy to do because then I'd have to put a different, well, I can't put it on these slides as they are now. I'd have to change it. But the shale has a higher velocity and density than the sand. So let's look at what happens. This is the reflection coefficient. Over here, if I had a shale, I have nothing, right? So there's no reflection coefficient of a shale against a shale. That's 0. And as I move along this curve, this tells me what that clean sand looks like, laminated. So over at this end, it's a pure clean sand, and I have what? About a 0.08 reflection coefficient. Okay, minus 0.08. I told you yesterday, 0.05 to 0.08, that's common, kind of a reflection coefficient in soft rock country. And what does this tell you? It tells you that, gee, I can alias an oil reservoir that is in a 60% net to gross rock. Looks like, has the same response as a clean sand, brine saturated. That looks the same. Seismically. That's what this thing is saying. And it says that, golly, if I look at this guy, or maybe this guy, 60 or 70% sand with gas in it, looks like an oil reservoir. So I've got a new caveat for you. All this hot air that I've been talking about all has to do with, it's not quite as simple as the simplest models. There's another thing that can catch you, and that is maybe what you think is really quite nice commercial possibility, and in between amplitude. Remember yesterday we were talking about, don't just look for the highest amplitude. Once you've seen that you have amplitudes and you expect them in the best quality rocks, start looking for intermediate amplitudes, because they could be oil reservoirs. Well, they could be oil reservoirs. They could also be gas reservoirs in crappier rock. That's not so nice, is it? The good news about the laminated, the fact of lamination is that the clean members, a 70% net to gross ratio, can be a very nice reservoir. It has good permeability. The permeable members have excellent permeability. And so there are some slides, I think they're in the appendix, that Gary Ostroff made in the summer when we gave this course in Houston. He made 2 or 3 slides, and I'll urge you to take a look at them. He has some calculations there of how you really will mess up the permeability if you do what I did for the velocity here. That is, calculate a bulk permeability as if this was a homogeneous rock. You get a permeability that's something like close to 1/10. I think it's 1/8 or something like that of the true permeability for a particular case that he ran. It's not unreasonable.
Let me just go and sort of amplify, that stuff. And if people are interested, when you look through those view graphs and want us to explain this, we will definitely do it. There's probably an exercise where you're going to be doing some of these calculations. We ask you to sort of make this mistake But, I mean, I want to be, this is something that I've run into again and again, and there are even certain vendors out there, such as Rock Solid Images, that I don't think understand this and routinely make a very big mistake. And so I'm really going to go and put a big line underneath this. I've seen it so much that if you mistake a laminated sequence for a true homogeneous rock, and you say, well, all this crap, and what you're really saying is all this crap, which is the shale, rather than being laminated, I'm going to like sprinkle it like the Pied Piper, you know, throughout the rock. Okay, that Gary shows. First of all, you end up saying the porosity is a lot less. Okay, so the volume gets to be less. Okay, what's even worse is that permeability. Okay, that if you go and relate to it. Okay, that you realize that if you have lower porosity, normally you'll say those rocks will have lower permeability, okay? So they'll flow less. But then you make it even worse is that if you go and have smaller pore throats, you say that you have lower oil saturation, okay? So let's go and take a look at what we've just done. We've taken the rock, okay? First of all, we've said there's a lot less pore space. Then we say there's a lot less oil in the pore space, and it's going to be a lot harder to get this out, okay? And the recovery factors are going to even be less, you know. And I call it exponentiating pessimism, because each of these are maybe a 0.8 factor, you know, except for the permeability, which is an order of, which actually, so you have a couple 0.8 factors, and then to throw insult to injury, you throw an exponential factor on it, which is the permeability at the end. And, you know, that, again, I mean, I saw, you know, for instance, I was at a farm-in, you know, for Statoil, to some Venezuelan acreage. And they said, hey, look, you know, here is, you know, we went and looked at it and the porosity was 15%. Well, I looked in it, I mean, this was even at log resolution with blocky sands. And at the block, it was obvious it was a 30% porosity rock. And I said, no, it's 50% net to gross over, you know, a 30-meter average of 30% porosity, you know. And so this is a big mistake that gets made. And one thing to sort of perk up your ears about, if someone starts using the word, and we'll go about this, called total porosity.
That's coming next.
That's in, Dave's going to get into that. That should be an alarm bell that they're misunderstanding, many times that they're misunderstanding the laminated line. So.
I think, in fact, I'm thinking that's the next slide.
Yeah. Before you get there, just one other point I wanted to make on here is that if you remember, this is distinctly different in character when you have this laminated mixing model from what you saw for gas saturation. Because of the effect on the velocity, that's very nonlinear, right? You got most of your effect right here at the beginning, okay? So this, if this was the other case, it would go up almost, you know, immediately and then not change very much, okay? That with respect to net to gross, okay, that this is what you really care about. It's gradual and is much more linear than saturation is, okay? And that's another thing to keep in your mind. Another thing, though, that saves you, and I want to go through just a little bit here in terms of this problem of, okay, you know, Dave showed that, okay, a lower net to gross oil sand looks like a brine sand, okay? Okay. Can someone go back to that Brunei example and remember where I sort of showed that you ended up having that nice contrast and fit the structure, but in the upper right-hand corner there was, you know, a brighter amplitude? Can anyone sort of explain that now from this graph? Can you sort of think of how you would explain that? Yeah?
Pretty easily when turbidites dump out, you know, you can have the poor quality fringe facies on the margin, and then you downslope you'll get some very blocky and clean sands that would fit that quite easily. And that's what we see in the Exmouth Basin as well.
Yeah, and you probably saw that bright amplitude I was talking about. You said it'd be the higher net to gross spaces, right? Yeah, and so that what you ended up seeing was in that bright thing, it was actually up here, if you remember right, and you have some visual memory. That was that high net to gross brine sand, okay, which is okay? Then, if you came across here, that was the same amplitude as a lower net to gross oil sand. But then when we went directly up dip of that, and what I said was genetically similar to it in its depositional facies, you went up to the brine sand, okay? So you went from that bright, okay, thing that didn't fit structure to something which is lower net to gross, which actually fits structure as you went down to the brine. So you need to be very careful, and the way that you get around this is that, you know, in terms of this net to gross, is always make sure, and we'll see that we start comparing something immediately up dip and down dip of the fluid contact that we feel is the same depositional type unit. And you do that so that you end up being in the same sort of vertical line, or going from here to here or here to here. And another thing you may try, and you'll see, is that the ratio of here to here and here to here and here to here is roughly constant. So if you stay in the same net to gross facies, going up dip, down dip, you know, another thing you hear in the industry is A to B ratios, okay? Up dip, down dip, right? You have to go and try to make sure that those things will be the same net to gross that you're grabbing.
And that's not, I'll just make a parenthetical comment, as in the example that Mike was referring to, you will remember that node, or that, you know, you had truncation here, that was up dip, and down here was down dip like this, and he was talking about that yellowish green
Yeah.
amplitudes up here, and down dip we have these yellowish green amplitudes, which were then oil saturated, same amplitude, two different rocks, and then as you moved up dip to that truncation, we got into some oranges and reds. That was the clean rock with the goodies in it, okay, with the oil in it. So you went back to this, I guess.
Yeah. And also, I mean, this is
But
why,
not to
when we
this,
say
but
it's
to
quantitative interpretation, okay, that, you know, the word interpretation has very explicitly been put there because there are judgment calls, you know. You need to go, and geology is very important, that when you go and say that I'm seeing a change in amplitude going from this to this, but if I look at the architecture and take out that sort of change as I go through the fluid contact, does this actually look like it's the same depositional setting
Exactly.
in terms of its geometries? And that's is a very important interpretational aspect. And you'll see as we go through and start picking amplitudes, we call it how do you normalize your amplitudes, right? And that this is the most artsy, it's the most interpretive, it's the most thing that involves the most geology, but it really comes about in trying to pick on whether or not I'm really going from here to here,
Right.
or I'm going from here to here.
Yeah, the stratigraphic variation is there in almost all depositional settings at the scale of prospect size. It's very common. And so trying to do this is important, as Mike has pointed out. How you do it, how do you do this? We better talk to your geologist and ask him. I think this is high amplitude that may be related to direct hydrocarbons. Tell me about the orientation of the depositional system. Where is the equivalent rock outside this anomaly, and how much facies variation should I expect from here to there? That's the guy you want to talk to. He's got the specialized knowledge. You heard Tim talking about this stuff, and you heard all the words coming out, spilling out of his mouth, because he's thinking in terms of how those systems work. And that's what you need to do, is tap the expert understanding of the specialists in whatever discipline you have to, in this case, geology. Okay, agreement?
One question. You showed us the sample, laminated sample, 18 inches of core.
Yes.
Lots of layers.
Yes.
I just wonder how laterally extend these layers extend
They
physical
don't.
size.
You can't, how should I say this? I have a good friend, taught me something about geology many years ago, but I'm Rufus LeBlanc. He died this last year. And he was a deltaic guy, specialist, well known in the AAPG. And Rufus used to say something like this: vertical nervousness, lateral nervous means vertical nervous. So if you see a log which has this kind of nervousness, that's what he calls this thin lamination, et cetera, even in a deltaic system he was talking about, then it means that you will not be able to correlate those thin bodies for very far. Typically, you will not be able. In deep marine deposition, you might be able to, depends on what it is. But for the most part, you won't. These are events that happen because of particular quick surges. They are quick events, and they're over with, and that's it. So they're not widely distributed like a what do you call it, a marine shale thing. So the answer is, go back to that. I go back to that all the time. If you see nervousness in the vertical section on your log, what have you, or in your core, don't think you're going to be able to track that very far. So
Like tens of meters or a few
yeah,
meters?
yeah. Well, I wish I could tell you. I don't know, but it's not prospect size. I can tell you
Yeah,
that.
well, it's, yeah, you'll go and see in probably tens of meters that break down, I'd say, on average. I mean, some of the geologists can, but it does depend on the exact level of energy and the exact process of deposition. And in that nervous normally means higher energy in general is involved with it. But the one thing to note, like, there's a well-known caveat, which are levee deposits in a turbidite setting, where you can have a millimeter bed that goes for a kilometer. And that's one, in fact, it's one of the surprising cases, in terms of productivity. But that was the caveat that Dave was talking about. Any of the geologists want to add anything to that, or?
Sort of talking about 10-meter correlation length. The seismic is not going to resolve those sort of things. So what are you expecting on average, that will be the same sort of lamination
Yeah.
through the bed?
Yeah, the question is, that's why you want to know something about from the geologist about at least in my opinion, about the depositional character of the system. What's depositional strike? What's dip? Where should I expect this type of rock to be distributed relative to where I am? East of me, north of me, that's what you have. You have to appeal to those kinds of things.
Yeah, many times you'll find that, if you go and there's a correlation exercise that's done, and trying to follow markers around, and that there's an ordering of the cycles, and normally the larger order or thicker cycles or the bigger events you can end up following for longer distances.
Yeah, they get separated by deep marine.
There may be certain body, sort of gross bodies you may be able to follow for a few hundred meters, much thicker ones for a
Come up
kilometer.
here. Karen.
Yeah, you're getting out of my range.
Okay. I wanted to bring up this slide. Gabriella Schell discussed some things with reservoir engineers and log analysts at our request back before we gave the course here in June. And the result of this, at least one result of that meeting and our discussions with her is this slide. And there's a point to be made here. There are various kinds of porosities that petrophysical engineers and reservoir engineers define and use in their daily operations. And I've been talking about porosity from a mechanical point of view in terms of Gossman equation and what that means and how it might be treated. So I want to try to tie the loop here and get an understanding. So this is what Gabriella talked about in terms of how reservoir engineers talk about things. There's a matrix, solid, what I call grains. There's clay. There may be something that has clay minerals. Now, when they're talking about this, talking about clay minerals in the rock. They may be dispersed, and may be there in any way. If you look at the microstructure of clays, the clay minerals have electrostatic charges on them, and in between those clay mineral layers that have electrostatic charges, there is water, bound water. It's very tightly bound in the clay minerals, and it's very hard to get it out. Stress over a long period of time, enough stress can remove a monolayer of water. Usually there's one left at the end of that kind of process, but it's very tightly bound, and that's what they're talking about here when they talk about clay-bound water. Then there's capillary-bound water. You know what that is. You started with brine in these sediments, and as you bury them, there's still brine in there. Eventually, you get things hot enough, and if there's organic material thermal generation model says, oops, I expanded that, I broke the rock, up it comes because it's lighter until it finds a seal, and it displaces a certain amount of water that was in the pore system of the rock. That's why you have hydrocarbon reservoirs. But it can't displace all the water because some of it is a permeability and it can't overcome the capillary pressure of certain size holes in the rock, certain size throats. So you have a capillary bound water in your reservoir almost all the time. And then there's mobile water. That is water that will flow. And you all know that this happens because when you have water drive, for example, and when you get to the end of the life of a reservoir, what's happening is you get 10 barrels of water out for every barrel of oil. That's mobile water. And then there's a hydrocarbon. Then all of this is in what I would call, all of this stuff corresponds to the rock the way you would normally conceive of it. And then over here we have vugs. In certain kind of rocks there are, I'm going to call vugs, an isolated pore. That is, pores that aren't connected with any other pores. It turns out most common in diagenetically altered carbonate rocks, but really some vugs are connected to intergranular porosity if there's some left from the genetic character of the rock, or vugs can be connected over short distances, and you may intersect some in your wells. So the way I think this ought to really look is you ought to put these guys over here, and they ought to be somehow be thought of as connected with the matrix. But since they could be connected in principle, I guess they'd like to consider them in terms of process. You'll see a big question mark here. For the purposes of this slide, when you see the word vug, you should think isolated pore, not producible, not in connection with the rest of the pore system. In our Gossman equation, one of the things we said is you have to have to move. Okay? So vugs are isolated pores, and from a mechanical point of view, they have to be considered over here as part of the matrix, and you'll have to change the matrix elastic properties, a lower density and lower bulk modulus. How much lower? Well, we won't get into that here. We'll talk about that on the side if you have an issue about how to calculate that. It's not trivial. Okay, you could make some estimations though. Now, these reservoir engineers and log analysts talk about porosities in slightly different ways. And the reservoir engineers, they call everything from producible hydrocarbons to non-producible, to mobile water and capillary bound water as what they call total porosity. And they call effective porosity anything that can move to the wellhead. Okay, so move the water. Log analysts, what physical engineers I'm given to understand in the modern world, call effective porosity the same thing the reservoir engineers call total porosity. And they include the clay-bound water in the total porosity. So from a mechanical point of view, that is, in terms of Gossman and everything, our definition of what we have called porosity in the previous slides yesterday is closest to the reservoir engineers' definition of total porosity, or the log analyst's definition of effective porosity. Just some terminology.
Well, and also, I mean, let me just go and sort of say what the problem is that happens, and the reason why it can be a bit of a red flag when you start here. Whenever I heard people talk about total porosity, it's just a red flag, you know, in terms of be very careful about the terminology. Okay. One thing you want to have very clear in your mind, that whenever we talk about porosity in this course, we talk about this, okay? Okay? And, you know, we've described what we're talking about. Thing to be aware that there are many different types of porosities, and there are different people will use the same name for different porosities. Many times when someone starts talking about total porosity, there will be a log analyst, and they'll go and be talking about this definition, and they compound their mess up by they take all of the laminated clay and they also shove it into here, forcing the overall porosity down, okay? Because they'll subtract this by taking the laminated and expand out this section, okay? So again, be very careful you know, about what you mean and questioning people with respect to porosity. Again, I'm bringing this up because I don't know how many times when I've been out on farm-ins, and then when even internally we've been talking about it, we've gotten involved in these discussions. And whenever you get involved in the discussion, I would really suggest getting this picture out and saying, what are you calling porosity? Because what I want is this. You tell me what you're telling me in terms of porosity, and use this as a discussion aid.
Somebody tells you, that's the best advice you can get. Somebody tells you, well, my total porosity was such and such. When you hear that word total porosity, the first thing you need to do is to say, tell me what you mean by total porosity. That's what you want to find out. Okay? And that ensuing discussion will let you understand how to calculate things in an appropriate way. Okay, so what's the takeaways? Many classic reservoirs in both deltaic and also in deep water, your outer deltaic, your fringe kind of deltaic rocks have the same laminated problem. And in deep water deposit studies are composite rocks, laminated rocks, consisting of fine alternating layers of sand and shale or siltstone. Properties of these laminated rocks can be computed as a function of concentration if properties of the end members are known. That's why we try to pick end members on the logs. Laminated rocks have less of an amplitude response to fluid substitution than the clean end member rocks, and so gas reservoirs and laminated rocks can have similar amplitudes to oil reservoirs in clean end member rocks. That's important.
And we need to start going.
Let me finish this, Mike, then. Go ahead. You can go back to that. One cannot replace a laminated rock with a homogeneous rock with the equivalent average porosity or a porosity derived from the brine saturated density. That's the same thing, average porosity or determined for the brine. That was that series of slides we had the dashed curves on. And then reservoir engineers and petrophysical engineers have different terminology, but use the same terms in different ways. So find out what they're talking about when you're, I'm sorry, Mike.
Yeah, and also I think right now the term that we use a lot called end member, you probably really do, I think right now, probably have enough experience to know why we use the term end member. Because you look down the log and you find out where things are in the end over here, and where they are under there, and then everything in between is probably a laminated mixture between those two ends, okay? And that's really where that comes about. And also, some of you may come across the words Thomas Steiber, that the particular type things we've been talking about in terms of these laminated corrections with respect to reference end members sometimes ends up getting referred to as that, and they'll call it, sort of a Thomas Steiber correction for, quote, shaly sands.
Yeah, well, Thomas Steiber, I'll just give you a couple words about Thomas Steiber. Thomas Steiber is a method, a log analysis method, which says if I have a density log and a gamma ray log, I think I can estimate what the volume of shale is. In other words, 1 minus net to gross in a laminated rock. They're assuming laminated model, and they go at it. And let me tell you that there are lots of mistakes you can make quantitatively applying it. So if you hear that word, find out what they did. Don't just take the number and use that. Okay?
Yeah, I think that now's probably a good time for a tea time break. It's about 10. You'll get